This is an online learning (LMS) project. The task course is EE301 Communication Systems. Whole material of this course is redacted then dubbed by an American English-speaking TTS, text-to-speech, software, and put into this slideshow with animations for students to easily follow and understand. Instructor, Dr. Ali Kara. Reference book, Communication Systems, Simon Haken, Michael Moher. Pulse modulation. Pulse versus CW modulation. Pulse amplitude modulation, PAM. Time and frequency analysis. Reconstruction. Time division multiplexing. Pulse position modulation. Digital modulations. Sampling. Quantization. Encoding, PCM, and line codes. Pulse modulation. Analog pulse modulation has some advantages over continuous wave (CW) modulation. Firstly, power is concentrated on short pulses instead of generating signal continuously. And secondly, time intervals between the pulses can be used to place other signals, for example time division multiplexing, TDM, although it has its disadvantages. Analog pulse modulation requires large transmission bandwidth, used only for message processing of TDM and CW modulation, telemetry, and instrumentation control systems. CW versus pulse modulation. Here are some graphic examples of CW modulation. And now look at the pulse-modulated signals for the same modulating signal. Here PDM is pulse duration modulation. As you can see, the width, in other words, the duration, of the pulse is modulated. PPM is pulse position modulation, in which the position of the pulse is modulated. And finally, pulse amplitude modulation, which is what its name suggests. Pulse amplitude modulation, PAM, time. Now consider pulse amplitude modulation in time domain. M of t represents our message signal, where M of f is its spectra. Now consider a rectangular impulse response, which we will use to represent our message signal in a sampled manner. Now, we construct our signal to be transmitted, S of t. It is driven by the summation of M of t convolved with the transfer function H of tc, that the envelope is M of t, and the bold plot consisting of pulses is S of t. Here H of t can be chosen differently. Consider it as a direct delta function, then we have instantaneously sampled version of M of t. In general we say S of t is equal to sampled M of t, convolution H of t. Pulse amplitude modulation, PAM, frequency. Now we analyze PAM in frequency domain. This graph shows the amplitude spectrum of H of f. As you well know, convolution in time domain corresponds to multiplication in frequency domain. So, we have S of f equal to sampled M of f times H of f. Sampled M of f can be found by this equation. And finally, as we multiply H of f with sampled M of f, we get S of f amplitude. Question: ideal sampling. Consider the message signal MT 10 sinc square 10T. The signal is ideally sampled with this sample frequency, Fs. Find the minimum sampling frequency possible so that no overlapping occurs in frequency domain after sampling, and sketch the resultant sampled signal in frequency domain. Also, for the case where an inadequate sampling frequency is chosen, sketch the overlapped signal spectrum. Solution: take Fourier transform of the signal MT and find the message bandwidth. As you will see visually on graph, the sampling frequency Fs should be at least 2 times the message bandwidth, so that no overlapping occurs in sampled signal spectrum. PAM reconstruction. Previous slide showed how to construct a pulse amplitude modulated signal to be sent. Now we analyze how to reconstruct it once it is received. This is the general diagram of the PAM reconstruction. Equalizer at the very end is used to reduce the amplitude distortions. Now we will analyze this diagram step by step. First, see that from our results from previous slides, S of f amplitude is shaped like that. Its time domain representation S of t is directly fed to the reconstruction filter, assuming no imperfections are present to affect S of t, the received signal. Reconstruction filter H of f amplitude has this trapezoid shape. Multiplying H of f with S of f, we get, after the equalizer, the received message signal M of f, or in time domain M of t. Time division multiplexing, TDM. Multiplexing is used to share the same channel with different users, applications, packets, etc. There are several multiplexing schemes where channel usage among different users are regulated in different fashions, like frequency division, time division, code division, etc. Multiplexing idea should also take into account that once we multiplex several signals at the transmitter end, it should also ensure that it can be demodulated, or say demultiplexed without any ambiguity at the receiver end. This is the basic idea. Although the idea is simple, there are several concerns about multiplexing schemes. They include the effective resource usage, bandwidth, and energy, overall throughput, fairness, etc. Time division multiplexing, TDM, consists of the following: pre-filtering commutator, electronic switch, pulse modulator, pulse demodulator, decommutator, reconstruction filters. Pulse position modulation. Variation of pulse width in accordance with the message signal is called pulse duration/width modulation, PDM/PWM. Variation of pulse position in accordance with the message signal is called pulse position modulation. Analog communication systems. This is the basic block diagram of an analog communication system. Source can be anything. The transmitter, also called TX, either uses pulse modulation or continuous wave modulation. And the channel. Our transmitted signal undergoes distortion, interference, noise effects, etc. And the receiver, also called RX, takes the signal from the channel and demodulates it so that we can retrieve the message signal that was actually sent. Digital communication systems. This part of the digital communication system is the transmitter part. We have the formatting part, which also involves encoding. It takes an e-message signal and digitizes it. Then the binary string, or digital string more generally, is fed into a pulse modulator, where the string is transformed to a pulse train. After that comes the bandpass modulation, which we have seen in the earlier classes in detail. It takes the low-pass signal and makes it bandpass. After we get the bandpass signal, we send it over air, on cable, or on any other form of channel depending on the setup. The receiving part is now quite simple, as we have studied the transmitter part. Every operation in transmission has its counterpart in the receiver end. The signal is received from the channel. It is demodulated, detected, and then, using the inverse of the formatting we used in transmitter, the message signal is retrieved. Note that synchronization is also an issue in this type of communication, because the phase of the signal plays a key role in detecting and differentiating a signal from the others. So without a good knowledge of the phase, in other words, without an accurate estimation of the phase of the signal, it is very hard to correctly detect or estimate a signal. Format. Now we shall see the components of the digital communication system part by part. Formatting takes the information source, in any form, digital, textual or analog, and format it into a digital bit string. As you can see, different types of message signal undergoes different routines in the format. For example, if you have discrete elements of data, but not in any digital bit form. Say you have two distinct elements, apples and oranges. You can feed this information directly to the encoder and it gives you a bit string. In our trivial example, let us say apples is 1 and oranges is 0. So for every apple you get a 1 and 0 otherwise in the bit string. If you have an analog signal, first you sample it, then quantize it, meaning you discretize it, and then you can encode it to a bit string. Format, sampling. and in the following slides we shall see sampling in more detail. Remember that it is employed in order to transform an analog stream into a digital stream. Sampling of sinusoidal signal. These figures illustrate different sampling times used on a sinusoidal signal. The first, as you can see, uses the fewest samples, and its shape is somewhat different from the other two, although they are all sampled versions of the same sine function. As we will see later on, the sampling interval, which is the time between any two samples, is not chosen arbitrarily, but according to a well-established theorem. The idea of sampling is to keeping the information intact with using as few as possible sample points. Sampling process temporal. So, sampling in time domain can be represented as convolving the message signal g of t with Dirac deltas chosen with our own preference of period. Sampling process impulse. As we have seen in earlier slides, taking the sample's means in frequency domain, repeating the original spectra at every fs frequency interval. Example, sampling. So, here is an example. Take the message signal x of t. Its Fourier transform x of f is denoted in the adjacent figure. Now sample it with Dirac deltas separate at ts, which is called the sampling interval. Ts reciprocal is called sampling frequency, denoted by fs. Here the first constraint on the sampling period arises. Fs must be larger than 2fm, fm being the bandwidth of the message signal. Multiplying in frequency domain, or convolving in time domain the Dirac delta train, and the message signal, we get the sampled x signal. Here you can see the immediate result of taking the sampling frequency fs larger than or equal to 2 times the bandwidth. If we hadn't have done it, in the final spectra the repeating amplitude spectrum of x of ts would overlap. We avoided it by a well-chosen fs. Sampling, rectangular. Here we see the same procedure with rectangle-shaped sampling function. It is more realistic than the Dirac delta because Dirac delta is not an achievable waveform. But the idea is the same. Question: sampling. Consider a message signal x t equals sinc 10t. Assume that it is perfectly sampled with the lowest possible sampling frequency. Find that sampling frequency, fs, and sketch the resultant sampled signal spectrum, x, s, of f. Solution: the lowest sampling frequency that is possible without any distortion on the message content is twice the bandwidth of the message signal. When the message signal is sampled perfectly with deltas, the resultant spectrum is just the repetition of itself every sampling frequency interval fs. Note that, for better visualization, there is a small gap between the repeated message signal spectral contents. Normally, given this rectangular shape in frequency domain, there is neither a gap nor an overlap between repeated spectrums. Sampling frequency, Nyquist rate. Now we come to the Nyquist rate, which tells us the limit of minimum sampling frequency. It is shown in the literature that by taking fs at least 2 fm, we can avoid overlapping in frequency domain. So reconstruction of the analog signal becomes possible. Aliasing. Aliasing occurs when the sampling rate is less than the Nyquist rate. The overlapped region contains the aliased part of the spectrum due to undersampling. Aliased spectral components represent ambiguous data appearing in the range of frequencies between fs-fm and fm. Example, aliasing. Here you can see how distorted the resulting spectrum if the sampling frequency is chosen to be less than 2 times the bandwidth of the message signal. Format, quantize. Now comes the quantization part. We saw sampling previously that took the analog signal and extract discrete points out of it. As the nature of the analog signals, after the sampling we may end up with infinitely many different sample points, which is quite impossible to represent as a digital string. Therefore, we need to do something to reduce the number of possible outcomes of this process to a finite number of points, which we can then encode. Format, Quantization process. From Sklar's book, the idea of quantization is simple. Take the set of samples and match them to some window so that you get a finite number of quantized points at the end. In this quantization process, we see that windows are chosen to be linearly separated, which means that any sample value falling into a window will be matched to the nearest quantization level. These levels are in this example linearly separated. Quantization, sine signal. Take this example of the quantization of a sine wave. Number of quantization levels is given as 2 to the power L, where L is the number of bits per sample. Question: quantization. For the message signal, mt equals sine 2 pi 1/6t, we wish to use 2 bits per sample to quantize the sampled signal. Find the quantization levels, and for a period of 6 seconds, quantize the signal assuming sampling frequency at Nyquist rate. Solution: 2 to the power bits per sample is equal to 4 when we use 2 bits per sample for quantization. So, we have 4 quantization levels in our hand. For simplicity, assume we use uniform levels. Pick the levels so that the interval between the minimum and maximum levels of the signal m of t is separated uniformly. That corresponds to a quantization interval of 1/2. Pick a random starting point for sampling, and find the sample points. According to the quantization levels, map them to the nearest quantization level. Note that where you begin quantizing doesn't matter, so long as you are in the 6-second interval. In this example, the starting point is chosen randomly as 1 second. Format: encoding. Now we study encoding. Encoding. From Sklar's book, in its simplest form, we assign a bit stream to every quantization level and call it encoding. In this example we have 8 points of quantization, therefore we need 3 bits to represent 8 different numbers. The PCM sequence is arranged in a way that the actual value of the quantizated sample is directly represented in the encoding, meaning the smallest value in the quantized samples, which is -3.5, has the smallest bit stream, 000. Question: encoding. For the message signal, mt equals sine 2 pi 1/6t, we wish to use 2 bits per sample to quantize the sampled signal. For a period of 6 seconds, encode the quantized signal into a bit stream. Use your results from the previous question. Also, determine the bitrate of this system. Format: pulse modulation. Now we come to the pulse modulation, which is the transformation of bit streams into physical pulse-shaped waves. Digital pulse modulation line codes. Here, the waveforms are line codes. The first type we see is holes and spaces. This is the basic digital data representation, which can be seen as holes and spaces on a piece of paper. We see that the abstract values 1 and 0 are now physical quantities, represented by holes and spaces on some physical media. Electrical examples are unipolar and polar no return to 0 codes. Here 1 is represented by some level A, and 0 is represented by its antipodal counterpart or 0. Digital pulse modulation line codes. In this figure, you can see more line codes, which are of type return to 0 or Manchester no return to 0. Question: digital pulse modulation line codes represent the bit stream 1100 by Manchester NRZ type line code. Assuming bit duration of 1 second and amplitude of unity. Format: pulse code modulation, PCM. Here is a block diagram of an analog to digital converter. Question: format: pulse code modulation, PCM. Consider the message signal mt equals 1000 sinc square 1000T. Find the minimum sampling frequency possible that allows perfect reconstruction. If we use a quantizer that represents every sample with 3 bits, what is the bitrate of the sampled signal stream?